Good afternoon and welcome to yet another virtual conference and virtual session. We'll be going over detailed rain on mesh to inform post-fire emergency preparedness. So this is a project we did for Boulder County. Excited to share with you. My name is Jeff Ullman and I'm also presenting with Kyle O'Neill. Before we jump right in, a little bit about myself. I've been with Baker for a little over a year. I'm a project manager here. I have 5 girls and a wife. And that's a picture of us in Yellowstone. Had a great time there. I'm also one of the team leaders at Baker, and I enjoy working on pretty much anything innovative. I really enjoy 2D modeling, project management, and client engagement. And we had a great client working with Kelly Watson. She's a floodplain program planner at Boulder County. And a little bit about our presentation. I'll share with you project background and purpose. I also want to overview some rain on mesh basics. What is it? And some pros and cons for those who may not be familiar. Then Kyle will speak to model construction and go over some examples. And then I'll conclude our presentation looking at some results and possible applications.
Thanks, Jeff. My name's Kyle O'Neill. I'm a civil associate with Michael Baker. I enjoy H&H modeling, computer programming, and developing solutions to unique spatial problems. In my free time, I like to snowboard, mountaineer, camp, just about anything outdoors, really. Today I'll be talking about the model construction, post-fire factors, and the simulations that we ran. But for now, I'll hand it back over to Jeff.
So a quick rundown of why we did this project. It was namely to identify structures, by that I mean culverts and bridges, that would likely overtop over a range of possible storms. So this was for the Office of Emergency Management to use to give them advance warning or kind of preview into what types of storms would close down a road, what you can see in like the upper right hand corner. That's the situation they're wanting to avoid. So they would close down the structure or even the road leading up to it beforehand and have this information in order to prepare for that. So we evaluated peak flows and elevations for a wide range of storms varying between 1/4 inch to 3.75 inches for a 1-hour storm, assuming that these are, the standard convective thunderstorms that would come through. So just, that upper range, we're looking at something greater than a 500-year event. So these are improbable at this point, but with post-fire conditions, the question was, what kind of flows could those generate? And you can see a picture there showing that bridge with, some of that ash and debris that was put up against it. So the project in essence was building a library that could be used for event matching when they look at a forecast, understanding what to expect, then they could go out and ahead and preemptively close these structures to keep people safe. I'll just note that this was a pretty quick project. It was executed between mid-March to the end of May. So it was a fast burn in that regard. And there's more information that you can find at that link there. So our delivery, I mentioned, May 25th was actually very timely because this was just days after delivery. This was Memorial Day when there was a decent rain event. I think this was 3/4 of an inch that fell. And you can see these are some pictures on the left here. You can see that's in up Gear Canyon, and obviously the upstream end of that culvert was completely clogged and overtopped. And then on the right-hand side, that's actually on St. Vrain after the confluence of North St. Vrain and South St. Vrain. And so we were able to have this information ready to be able to use before the summer thunderstorm season took hold. As for the fire itself, it was in October to November of 2020. It burned over 10,000 acres and many structures as well. It covers portions of 4 hucks. You've got 1, 2, 3, 4 here. It essentially burned all of Gear, at least the upper portion of the watershed. So you get a very quick, flashy response coming down into the left-hand creek here, whereas Central Gulch, it burned the middle portion, but not the upper portion, which was interesting because when we were looking at inflow hydrographs coming into South St. Vrain here, we'd see a dual peak. And that's because you get a flasher response from the middle and then a slower response up here because this had higher Mannings and lower curve number. And so what we did is we looked at structures along St. Vrain and along Left-Hand Canyon all the way down to Nimbus Road and St. Vrain all the way to US 36. This slide is going to give a quick crash course in rain-on mesh methodology. Sometimes it's called rain-on grid, though that implies a rectangular cell. And then often this is what's used for 2D BLE or base level engineering. But like any good model, it's going to rely on good terrain. So we build a digital elevation model. And then we divide up our model into domains based on hydraulic basins. And then sometimes take into account different land use parameters and spatial patterns, although now RAS 6.0 is able to account for that internally within a layer. So it allows for larger basins like you'll see in our model here. Then you overlay it with a mesh and you can vary the nominal size. You can refine it based on features like streams. The most importantly, it's going to be your high ground because that's where all the calculations happen across is your break lines. They align your cell faces. If you're not familiar with 2D modeling, in essence, it's kind of like you take a bunch of storage areas and connect them with 1D cross sections, but it's based on volume instead. And then once we have our model ready to run, we'll apply different rainfall scenarios to it. Ideally, if you have a historic one to run and simulate and you can calibrate against known data like gauge records, you could validate within a tolerance range for regression equations, but I wouldn't recommend actually directly calibrating to them. And once you have a calibrated model, then you can run your simulations. So if this is 2D BLE, you typically do your 6 or 7 standard FEMA ones. For what we did, we ran 30 different simulations, basically 15 post-fire and 15 pre-fire. Here are a couple examples of layers that would be used in a rain-on mesh model. That is the essence of how they're structured, is you have different layers associated with it, and then you lay your mesh on top of it, and it's reading the underlying layers. So on the left is Manning's End. That's a combination usually of land use, and then we'll tweak it based on calibration. We'll do overrides also based on where stream channels are. And then on the right-hand side, this is a newer feature within RAS 6.0. You can actually do infiltration, and here we're showing curve numbers, so you can actually do losses within HEC-RAS. Previously, you had to do that like in 507 outside of the program, either in HMS or in some sort of a spreadsheet. But now it'll actually do it within HEC-RAS, and what's great about that is like this, for example, is at a 10-foot cell resolution, so you're getting really high detail in terms of loss calculations at each individual cell. Here are a couple examples of how you might refine your mesh based on the presence of structures. So on the left there, if you have maybe base level, or if it's not an influential hydraulic structure, you can just modify the terrain. That's another great addition to RAS 6.0 is rather than having to use a V-notch break line, you can just put in a terrain modification and it'll just burn it straight in, and you can set those the width appropriately as well. And then that way the break line stays on top of the feature. On the right, this is what we did actually for Calwood, which I think Kyle will expand on a bit more, but we kind of did like a limited detail rather than just base level, and we did this by extracting structures from the effective 1D models, and rather than building them in as individual structures, which increases computational time and it just takes more time to integrate, we integrated them in as rating curves that were basically taken straight out of the 1D models.
Thanks, Jeff. So our study area obviously encompasses the burn area itself, shown here in a red outline. But the entire model extends from the downstream area, where we have an interest in existing infrastructure, all the way up to the continental divide in the west. Extending up to the divide mainly serves to route stream flow, but also provides us flexibility in the future to incorporate changes to the basin itself or to easily add precipitation events, potentially those with spatial variability. Currently, the areas used solely for contributing flow to the model were built at a coarser cell size, either 400 or 800 feet. We used a 100-foot cell size in the detailed area around the fire and a slightly larger cell size of 200 feet in the area downstream of the burn. We also refined the mesh down to 50 feet in specific areas, which I'll get to in a minute. We built a total of 42 connections into the model. These were a mix of bridges and culverts, along with a few calibration points that were identified prior to model construction. We also added 45 profile lines at additional locations throughout the model. Since these profile lines can be added after we build the model, We were able to share initial results with some of the stakeholders and then get input on areas of interest. Many of the locations that we added after the fact were important roads identified by the Office of Emergency Management for Boulder County. At both the connections and the profile lines, we're able to predict flow, volume, water surface elevation, depth, and velocity. As mentioned earlier, we vary the nominal mesh in different regions from 100 feet up to 800 feet. We further refine the mesh to 50 feet around structures, stream center lines, and other areas of interest. The image on the screen here shows an example of that around a couple of structures in the model. The streams identified by the NHD Plus high resolution flow lines, along with ridge lines, roads, and any other controlling features were incorporated as break lines into the model. By iteratively running test flows through the model, we're able to ensure accurate break line placement in the mesh. In the model, we apply a spatially varied Manning's-N layer across the entire domain. By mapping an N value to a land cover type, we're able to take advantage of the National Land Cover database to get full model coverage. To do this, we sampled a number of locations within each land cover type throughout the domain. By looking at the aerial imagery, we came up with an estimated N value at each location. These values are sample points, which are then averaged to come up with a single N value for each land cover type, providing a broad coverage across the domain. We further refined this Manning's-N layer by creating segmented stream buffers that produce a more localized N value by applying a spatially weighted average of stream channel roughness and that of the immediately surrounding area. You can see an example of these refinement areas following the stream network in the example here on the screen. For the post-burn scenario, we applied N values broadly across the burn severity classifications. A Manning's N value of 0.08 was assigned to the low severity burn areas, and a value of 0.033 was assigned to the moderate and severe burn areas. A spatial intersection between burn severity and the pre-burn Manning's-N layer was used to ensure that roughness was not increased under the post-burn scenario. That being said, we did account for a slight increase in post-fire channel roughness resulting from debris, and that was incorporated again into these refinement regions that you can see on the screen. To model infiltration, we utilized the SES curve number method, which is an option in HEC-RAS. Similar to the Manning's-N layer, we produced a spatially varied curve number layer across the domain. Using a spatial overlay of soil hydrologic group from the Surgo dataset and land cover type, again from NLCD, we assigned a distinct curve number to each unique land cover soil type combination. This produces a spatially varied curve number layer that you can see here on the screen. Curve numbers were updated to reflect post-burn conditions based on USDA guidance. Typical post-fire curve numbers were identified from a study that focused on an area in Colorado that has similar characteristics to the Calwood fire area. Post-burn curve numbers were calculated based on a combination or a spatial intersection of land cover type, hydrologic soil group, and burn severity. Additionally, the abstraction ratio, which relates potential maximum soil retention to the initial loss, was dropped from the typical value of 0.2 to 0.15 for low severity burn areas and 0.1 for moderate to severe burn areas. As mentioned earlier, the area in the model upstream of the burn contributes stream flow to the basin. This area covers the headwaters of Left Hand Creek and South St. Vrain Creek, which were calibrated separately. Typically, we would set a calibration region polygon to match contributing drainage area to a gauge and then calibrate to that gauge. Since this area has sparse historical data, mostly inactive gauges, we used CHAMP HEC HMS hydrology model that were calibrated to the 2013 flood event. We ran the predictive storms from that HMS model through our model and calibrated our model to their peak flows. So we calibrated to a calibrated model. We did this by adding a number of calibration regions that correspond to the subbasins in existing CHAMP hydrologic models, which you can see here on the screen. The curve number values, originally calculated using the method I described earlier, were then scaled to adjust the flow results in our model. Where possible in the calibration process, the calculated curve number values were scaled to roughly match those in the HMS models. Once we had a calibration model, we ran 30 predictive simulations. These were pre and post burn scenarios for each of the 15 rainfall events listed here. We varied the simulation time based on peak flow timing. Where possible, we shortened the simulation time, ensuring that the peak flow made it all the way through the model, but not running much past this, which would create longer run times and larger file sizes. In general, the run times were reasonable, ranging between half an hour to an hour. And now I'm going to pass it back over to Jeff, who's going to discuss the results of these runs.
All right, thanks for going over the model, Kyle. So that's something that if we were in person, we'd love to do like a quick demo or something, kind of nerd out on some of the engineering details. So if you've got a specific question, feel free to put it in the chat and hopefully we can get to it in the Q&A. So for here, I'm just going to go through some quick screenshots of example results with the caveat of I'm going to focus it on what we were using, knowing that RAS 6.0 has a lot more data that you could actually present or extract from the model. So as Kyle has showed on an earlier slide, there were a bunch of connections that we had put in at known structures. Some of these were private crossings, but they're mostly county roads. And there were areas of interest where we were going to extract results from. So at those locations and then random cross sections throughout, so we'd have a representative sample, we drew profile lines. So within HEC-RAS, if you're not familiar with it, you can extract pretty easily out of RASmapper by just drawing a profile line that is perpendicular to flow, and from that you can get a flow hydrograph, stage hydrograph, you can get velocity, you can get volume accumulation, but also in the actual internal connections which we built in the structures, you can see that on the southern part of the picture on the left there, it'll automatically output a hydrograph. So that's what you can see on the right. So basically, we built all of this into our model beforehand, before we did all the simulations, so that that data would be automatically aggregated and we were able to work with that then in a spreadsheet form. Before jumping straight into the results, I did want to touch on another thing we were able to do. If you recall, I mentioned shortly after we delivered the data on Memorial Day, there was a flood that came through. So we were able to look at some of those pictures and kind of do a rough model verification, just a truth check based on actual recent data. So you can see in this picture here, where there's kind of that line of ash going across the structure. We're able to estimate the depth from these pictures, and then draw a cross section or a profile line at that location, which is obviously denoted by the truck in the background of that picture there, and come up with a rough depth estimate across that channel. So we looked at different instances, and if you look at 3/4 of an inch, which is what was estimated to have fallen, it was roughly between 3 and 3.5 feet, which is represented in the photo behind. So we felt like this was a convenient, unplanned model verification check. As for the data that we actually delivered, our focus was 3 main variables. So the peak flows, both total and what's going through the structure versus what's overtopping, and then also a pre versus post fire assessment of that. We looked at the maximum depths of what's on top of the structure itself relative to the deck, and then also along the road, like approaching the structure, because it's no good if the road is inundated, even if the structure is high and dry, and then also the max depth in the channel. And then we provided information on time to peak and time to overtopping, so that they would know, the OEM would have an idea of which bridge they would need to close first, and then also overtopping duration, so they had a sense of how long it would need to be shut down for. In terms of data format, we provided spatial files, provided the model, some Excel tables, which I'll briefly show later, graphs, curves. We can use this to provide inundation maps. Again, that's in RasMapper. And then this was all used with Boulder County in-house to create an interactive web map. So here, this is an example, I guess, of maybe the results in its most basic form of what they were interested in. And so it shows a list of different structures or crossings. And these two columns here, the middle one that says closed structure, we had a tolerance of anytime there was less than half a foot of freeboard, they would close the structure. So this shows the depth at which that would occur. So on these top ones, at 1 inch storm post burn, would create less than half a foot of freeboard, and so on down the roads there. The one on the right, close the road, is similar. It's saying if it got 1 foot deep or deeper, you would close the road. So then you could use this as a cheat sheet to say, hey, we're going to have to shut this road down, the Gear Canyon at High Valley Ranch there, if you get 1 1/4 inch of rain. This is a more, I guess, thorough view, same data, but it's showing for each of those scenarios. We had it post-burn and pre-burn, which is off the screen to the right there, but kind of like a simple stoplight format in terms of, green, you should be good. Yellow, you might want to check it, and red, yeah, you'll definitely want to close down that road. And so we gave the depth intervals, or in terms of depth in inches per storm, it shows how much freeboard there was left here, or overtopping depths. This is a spatial depiction of showing actually a change in percent flow. Just thought this would be interesting to show. You can see in the burn areas, especially higher in the watershed, there's some significant increases for a fixed scenario. So these are both showing a 2.5 inch over 1 hour storm duration, which is equivalent about with a 1% depth, just looking at the NOAA Atlas 14. But you can see there's changes of 400% increases within the burn area, and then as it moves downstream, it has a mitigating effect and decreases. This is a similar way of looking at that. It's a profile along Left-Hand Creek above Nimbus Road, which was near the end of our model. And so you can see that sharp increase around 35,000. That's where Gear Canyon comes in. And then it actually decreases as you move downstream, because at that point it's taking up storage in the overbank and actually mitigating that peak as it moves downstream. This slide portrays how you might use other information within the model, such as expanding inundation extents. So again, our focus was on crossings, but you could also look at buildings and footprints and how that expands. So this just shows expanding inundation extent. You could do pre and post burn for the same one, or just incremented intervals and interpolate in between. This slide is meant to just quickly highlight other capabilities within HEC-RAS, and this is an example where you can add a results layer, a new map, and set a threshold in there and say, hey, tell me how long it takes until a cell gets to 2.5 feet deep or deeper. And so that's what's shown here. And if you look at the legend, yellow is about 2 hours. So, near the downstream end, it's going to take 2 hours before it reaches 2 feet deep, at least in the stream there. Whereas further upstream in Gear Canyon, it may actually be under an hour. To quickly highlight some other uses that you could use a rain on mesh model for, part of the reason, like Kyle mentioned, that we built it all the way up to the Continental Divide is for future simulations. If they wanted to analyze things, you could actually do different storm durations, distributions, and even storm patterns with movement in 6.0. Like I mentioned too, you can look at flooding extents. You can also look at different variables like velocity, duration, momentum, depth times velocity, which is useful in terms of understanding when people or cars could be swept away. You can put it in hazard classifications. Other uses that we did actually have this for was we shared this with a couple external parties or consultants that were using this for restoration and recovery efforts. So they looked at our data and helped inform their designs. And then you can also use information outside of the post-fire component, but just where you have, basically rain on mesh information anywhere that can help inform your stormwater capital improvement plan as well. I wanted to throw this slide in here really quickly just for those that might be interested in other post-fire resources. And I put on here predictive post-fire resources because you can actually do these analyses before it happens. That way you're prepared, you have that information. And one way you can do that is from the Colorado Wildfire Risk Portal. And this here shows the burn probability. So the likelihood, so you could actually forecast this scenario. And you can also download any of the historic burn scars as well. and I put the link on there at the bottom. Another place to get great resources is from After the Flames. I don't expect anyone to be able to read this list, but just get the sense that there's a lot of information out there. This isn't even all of it from that website. It's just a small screenshot. So I encourage you to check both of those out if you need more information on that. In summary, I think that Rain-On mesh modeling offers a lot of benefits. Just with its diverse inputs and capabilities, I think it can really be customized to your client's specific solution. I know it's used, widespread for 2D BLE, but I think there's a lot more that hasn't been done with it that can be in the future. So if you have any questions, I included our contact information below and would be happy to take them now. Thanks for attending.